Simple harmonic motion. There's one problem on our last problem set, and we're staying pretty close to the problem here. Suppose we have a block on a spring. This is my picture of a spring. And right here at x equals 0, it would be at 0 meters, it would be in equilibrium. We stretch the spring out, let the block go. Well, the block eventually is going to compress to negative a meters. If we stretch it to a meters, it's going to compress to negative a meters. And this is what we call a half a period. A full period would be back to its original position. This block would oscillate in the absence of friction, which is an impossible idealization. But if we had no friction in the spring, no friction in the air, no friction between the block and the surface, this would oscillate back and forth forever and ever, back to x equals a meters, and then back to x equals negative a meters, continually going through x equals 0 meters, which is called the equilibrium position. Just to recall before, we have our cosine solution, a cosine bt equals c. This is going to be useful. We have two solutions here, quadrant 1, quadrant 4, assuming c is greater than 0. c less than 0 is a different formula, quadrant 2 and quadrant 3. We have a situation. It turns out you can prove x equals a cosine squared of k over mt. We'll talk about k and m in a minute. You can derive this using Hooke's law. Hooke's law determines the spring force proportional to how far it's stretched, and also an interesting subject called differential equations. You can derive this. It follows deductively based on Newton's laws. It's an absolutely true statement, assuming no friction. We also assume that the spring has no mass here. The spring moving back and forth, if it has mass, that adds to the problem. If you want to add a correction, you can actually prove, you can take 1/3 the mass of the spring and pretend that it's embedded in the block, and it gives you an exact representation. You can prove that using calculus. We have a spring constant K equals 36 newtons per meter. Just to give you some sense of reference, we're not always used to thinking in terms of metric. A newton is about a quarter pound. If you go to McDonald's, order a quarter pounder, you should be able to say a newton, and it would be about the same thing. It's 0.2248 pounds, but about 2.25. So 36 newtons is roughly 9 pounds, and meter is about a yard. So you could change this to roughly 9 pounds per yard. So what that means is we have the spring. It would take us about 9 pounds to stretch it a yard, to stretch the spring. It's a pretty springy spring. 9 pounds, about 2 college textbooks, roughly. If you were to hang this vertically and put 2 college textbooks on it, it would stretch it about a little more than 3 feet. So, and we're going to put a mass of 4 kilograms. The kilogram is a unit of mass on the surface of the Earth. That weighs about 2.2 pounds roughly. So 4 times 2.2, roughly 9 pounds. We're putting a 9-pound mass here, ironically, about 2 college textbooks. So if you were to take these 2 college textbooks, take this and align it vertically, and just let it hang, it would stretch the spring about, stretch it about a meter. So we're going to stretch this out to 2 meters. We're going to assume the stretch has that much stretchiness, and it all depends on the size of the spring. So we need a pretty big spring to do that. I'm going to stretch it out 2 meters, let it go. That's going to, the spring force is going to accelerate. It's going to pass through equilibrium, compress an equal amount. You can prove that unless the spring bottoms out or something, but we'll assume it has enough room to compress as well. It's going to compress, stretch, compress, stretch. You can plug these parameters into the cosine function. 2, the amplitude goes here. K is 36, the mass is 4. Of course, square root of 36 over 4, square root of 9, which is 3, so we get a very simple cosine function. This tells us what the position is as a function of time. We can predict where this block will be when, and we can completely describe the system. You can actually find the velocity as well. Velocity ends up being a sine function, but we're not going to go that far. When you get to calculus, you'll be able to do that. When will x equals 1 meter? Well, if this is 2 meters, there's 1 meter right there, halfway in between. What's going to happen? It's going to pass through here, go to full compression, and then come back. So within the confines of one cycle, it's going to reach that point 2 times, one time moving to the left, one time moving to the right. And of course, it's going to do it again and again and again and again. It's going to follow this periodic fashion. We can solve this analytically just by plugging 1 in for x, and it gives you 1 equals 2 cosine 3t. And following these formulas, we end up with 2 solutions. This is positive. Inverse cosine 1 over 2, that's c over a. Inverse cosine of a half, which is an exact value, it's pi over 6, but you don't have to use that. Divided by 3, that's this 3, plus 2 pi over 3 times n. And you can simplify that. You can do that on a calculator. Make sure your calculator is in the radian mode. Gives you 0.349. And then 2 pi over 3 is 2.094, also done on a calculator. And then our second part of our general solution is 2 pi over 3 minus this, plus 2 pi over 3n. And if you can save a little bit of time, this is really that. So you can do that minus that, give you that. Then just copy that down. And this gives you the general solution. If it's going to pass through that point, it's going to be some value in the set of parameterized solutions. Now find the first 4 times in which x equals 1 meter. Well, we can let n be 0. You're going to plug n equals 0 in here and here. It's going to give you that time and that time, obviously. If you've done the previous problem set, you can see that. Well, there's the first one, and then there's the second one down here. And then, of course, when you let n equal 1, we're going to plug 1 in here and here. And then you add these 2 numbers together, add these 2 numbers together. And then you get this and this. So, and that's how you solve. That's how you put all this together. There's a lot more physics concepts involved here, but if you can handle the math, the physics concepts usually take care of themselves. So that's all for this video. We'll be back with some other information. I'll have another short video on this. We'll break it up into a second video. This is enough to do your homework. We'll have a short video shortly.